Hello, and welcome everyone to Perimeter Institute's public lecture series. My name is Emily Petroff, and I'm Perimeter's Associate Director for Strategic Partnerships, Grants, and Awards. I'm delighted to welcome you back to the Mike Lazaridis Theater of Ideas here at Perimeter Institute in Waterloo. Perimeter Institute was created to be a gathering place where people can come together like we're doing tonight, to ask big questions about the universe and search for the big answers. Perimeter will soon celebrate 25 years of bringing people from all paths together, researchers, students, teachers, and the general public, to explore the fascinating world of physics. But people on this land have been asking big questions about the universe for thousands of years. Looking up at the night sky and understanding our place in the cosmos is a fundamentally human constant throughout the ages. We acknowledge that Perimeter is situated on the traditional territory of the Anishinaabe, Haudenosaunee, and Neutral peoples, and is located on the Haldeman Tract, the tract granted by the British to the Six Nations of the Grand River and the Mississaugas of the Credit First Nation. We are thankful to those who preceded us, and we are committed to act responsibly and collaboratively to carry forward the quest for knowledge for the betterment of all. For those watching the live webcast, please join the conversation online. We are at Perimeter on Twitter or X, and Perimeter scientists are online to answer your questions. If you have a question for our speaker, ask it with the hashtag #PILive. This week, Perimeter is proud to be hosting a fascinating conference called Puzzles in the Quantum Gravity Landscape, which is bringing together experts in cosmology, black hole physics, gravitational effective field theory, and quantum gravity. The Institute is buzzing with more than 125 in-person attendees and many more joining virtually from around the world. And now, it is my very great pleasure to introduce one of those conference attendees and our speaker for tonight, someone who may be familiar to many of you. Born in South Africa, Professor Neil Turok received his PhD from Imperial College London and currently holds the Higgs Chair of Theoretical Physics at the University of Edinburgh, as well as the Carlo Fidani Roger Penrose Distinguished Visiting Research Chair in Theoretical Physics here at Perimeter Institute. In 2003, he founded the African Institute of Mathematical Sciences, also known as AIMS, a pan-African network for training the next generation of mathematical scientists. Professor Turok has had a distinguished career, including numerous awards. He asked me to keep it short, but I would be remiss not to name a few, including the John Torrance Tate Medal for International Leadership of the American Institute of Physics, a TED Prize, the James Clerk Maxwell Medal of the UK Institute of Physics, and he is also an Officer of the Order of Canada. In addition, as you may know, Professor Turok served as the director of Perimeter from 2008 to 2018, and he was the driving force behind many of the programs and projects that have made Perimeter what it is today. He led Perimeter's growth into one of the world's foremost independent centers for theoretical physics and launched, among other initiatives, the Perimeter Scholars International Program, which is a master's program here at Perimeter, the Distinguished Visiting Research Chairs Program, and the Center for the Universe. Professor Turok's research focuses on developing fundamental theories of origin and evolution of the cosmos, as well as observational tests. He has collaborated with scientific luminaries such as the late Stephen Hawking. Tonight, he will discuss recent developments in this quest to understand our cosmic home and the laws of nature governing everything, from particles to the entire universe. He will also explain how new measurements may soon test these exciting ideas. Please join me in welcoming to the stage Neil Turok.
Thank you, Emily. It's a real pleasure to be back here at Perimeter. I had such a lot of fun as director. It really was a unique opportunity. And it's just great to see it thriving today. So what I'm going to talk about is a new approach to tackling the secrets of the universe. And it's a new approach actually born, in a certain sense, of frustration with previous approaches. In my view, they'd become rather complicated and contrived, including my own approaches. And yet the data, whether it was coming from the very small or the very large, was the opposite. It was stunningly simple. You know, the world's most powerful ever microscope, the Large Hadron Collider, turned on, discovered the Higgs boson, which was almost guaranteed, and nothing else since. And so somehow nature has worked out a simpler way of being consistent than theorists had anticipated. So same story on the very large scales. Having mapped the entire visible cosmos, what we discovered is that the description of the cosmos is stunningly simple. It does not get more and more complicated. As you go to larger scales, it's the opposite. It gets simpler and simpler, apparently. So based on this, this really inspired me to try to devise simpler, more economical, more predictive, more principled explanations for what we see. And that's not easy. What I'm going to explain is very new, very preliminary. We've taken certain steps along a new route. And I'm here partly to expose these ideas to lots of experts. The Institute is full of these kind of people, at least the modern day equivalents. And this is very much the atmosphere at Perimeter. This may be the director of Perimeter. But I wanted to call your attention in particular. This is the kind of role I'm playing. This person looks like he's cheating. I am, because I'm looking at the answer, namely the universe and what we actually see from the observations. And I'm looking over the shoulder. This is Anaximander, and he's looking over the shoulder of Pythagoras. Pythagoras is figuring out the exact logical rules of mathematics. And Anaximander has one eye on that, so he's kind of okay at the math, but he's really taken these main clues from experiment and from the world. This person probably invented the concept of doing experiments to check scientific theories. So that's who I want to be. And over here is Euclid, figuring out the axioms of geometry. You know, we have plenty of mathematicians in Perimeter Institute as well. So I'm going to tell you about these very new ideas. I'm surrounded by all these clever people. And I must warn you in advance that it could be that these ideas fall apart tomorrow. Somebody here may point out some serious flaw, and the whole theory will fall flat on its face. And I do apologize in advance. Okay. But I don't actually think that will happen. I hope that won't happen. But if it does, so be it. Good scientific theories are testable, either through logic, a logical argument, or through measurements. And one has to just celebrate when they fail and move on. Okay, so we live in a spectacular universe, and for some reason we don't understand. It literally tells us its secrets. The ways in which the laws of physics have been discovered illustrate this again and again. And so, obviously, we live outside the sun. It's spectacularly beautiful. One of the main laws of quantum mechanics, Planck's law of radiation, that radiation comes in packets of energy, is illustrated perfectly just by the color of the sun. And so all we had to do, really, to figure out that light is quantized is just look at the sun. Now, we live inside the Big Bang, and the Big Bang is very similar in a way to the sun, except that we're inside it rather than outside it. The sun's temperature is about 6,000 degrees. The temperature of the spherical shell in the universe that emitted the radiation we now see from the Big Bang, that shell was about 3,000 degrees when the radiation was emitted. So only a factor of 2 different from the sun. So our place is outside the sun, but inside the Big Bang. And both of them are shining with light according to the most fundamental principles of physics. So here is the first breakthrough satellite in 1992 that measured the radiation from the Big Bang with very high precision. And you see the curve here. This Planck spectrum is the most famous curve in physics because it's the origin of quantum mechanics. So Planck figured this out from electric light bulbs, fitting the data in order to predict the color of an electric light bulb. But the sky, it turns out, is shining with exactly this spectrum. It's based on ideas of heat and thermodynamics worked out by Boltzmann, this exponential law that the probability of getting an energy E is given by exponential minus E over K Boltzmann T. So it's and that describes this tail of the distribution at high frequency. But more important, the energy is given by Planck's constant times the frequency of the photon. And so the whole universe is literally shining at us with the elementary spectrum of quantum mechanics, telling us that light is quantized. It's an amazing fact, and the error bars on this curve are minuscule. In fact, the cosmic black body radiation is the best black body we know of in nature. It's very hard to make an artificial one anywhere near as good. In fact, we could have learned this from the sun if we were able to observe the solar spectrum. We can't because of the atmosphere. So the atmosphere creates lines, absorption lines. This spectrum is the extraterrestrial solar spectrum. That's if you get above the atmosphere, this is what you see. And it also fits the Planck black body spectrum very, very well. So again, you could have learned this just by looking at the sun. We've just had to get above the atmosphere to do that. Here again are the theoretical curves. This is at 5,000 degrees. It's emitting colors which are yellow and red. As you lower the temperature of the sun, it would get redder and redder. This is classical theory, which is absolutely hopeless. And so quantum theory gets the right answer. So the universe literally tells us its laws, and that's the fundamental thesis of this lecture, is that we have to look at the incredible array of data we now have, figure out which parts of that data are really telling us something fundamental, and learn from that. So here is Planck's basic postulate. Planck didn't come to this postulate easily. He said this was an act of desperation to try to make sense of what was going on. The problem is that if you know that light is a wave, waves come in many wavelengths, and you can fit small waves into a given volume in a huge variety of waves. Just imagine putting a wave of a certain length into a box. The smaller the wave is, the more ways there are of distributing those waves. And essentially, the problem they had in thermodynamics is that if that's really the way light worked, if that's all there was, that light was waves that could be any amplitude and any size, you could just fit vast numbers into a box. Now, the light in the sun is basically in a box because it's scattering off the particles. It takes about 100,000 years for a light wave emitted in the core of the sun to get out of the sun. So this light is rattling around for a very, very long time. And if it was true that it could literally grind itself up into arbitrarily short waves, the sun couldn't possibly exist as a stable object. You would just grind all the light waves up into the shortest possible waves, and the sun would disappear in a flash of extremely short wavelength radiation. You need quantum mechanics to stop that. The quantization of the waves in units of energy, in particular that the short wavelength waves have to have a certain amount of energy to even exist as a piece of light, a photon. That is what stops this runaway into very short wavelengths. So he came to this postulate. It's what allows the world to exist stably, and objects like the sun. So it's very, very fundamental. And here it is. So the energy of a light wave is given by a constant times its frequency, and the frequency is related to the speed of light and the wavelength in this way. So short wavelength photons have a lot of energy. And you sort of feel this, you know, when you listen to the radio waves are passing through you and the room and everywhere, and we don't feel a thing. But if you stand in a bright sunlight, obviously you're feeling that radiation. The radiation comes in high energy packets, and that's why X-rays or gamma rays are dangerous, because each packet of energy can do something destructive to the molecules in your cells. So here we are inside the bang. And as we now look out in more detail to this shell of radiation which is coming at us from the Big Bang, you see this random pattern. And this was first mapped initially by COBE at very low resolution, but then by this Planck satellite. And so it looks like just a random pattern of waves. Somehow what came out of the Big Bang was pretty much like this, just a random pattern of ripples. The ripples in this case are the density of the universe. It varies slightly from place to place, and so does the temperature as we see this surface emitting radiation. So, but it's anything but random, because, so it is and it isn't random. It's random in the sense that the precise location of the waves is random, but the spectrum of radiation of the waves, just like with the Planck spectrum, is very, very precise. Okay, so this power spectrum means if I look on a certain angular scale given by this formula, then as I vary the angular scale, the strength of the waves varies according to this very precise curve. And these features on the curve are really nothing surprising. They're just the sound waves in this hot plasma that came out of the Big Bang. They have a characteristic scale just to do with the speed of sound in the plasma, and that causes these peaks and troughs. So this curve was predicted long before the observations by Jim Peebles, among others. Jim Peebles won the Nobel Prize for predicting this, among other things. I was very fortunate to be the first to calculate this curve, which is the curve of the power spectrum of polarization of light coming from the Big Bang. The experts in the field had published papers saying that this was 0, but we realized that didn't make any sense, me and my postdocs, and we calculated this. And amazingly, this curve is a prediction with no free parameters. If you adjust the cosmological parameters to fit this curve, then this curve is absolutely predicted. Okay, so this was one of the first influences on me, telling me something, whatever's going on in the universe, it's really simple. Okay, it's not arbitrary. It's the laws the universe obeys are truly universal, and if we get them right, in this case, the laws that go in here are Einstein's theory of gravity and the laws of plasma physics, which were worked out in the 1920s, a long time ago. So here's our model of the universe called lambda CDM. It has just 5 fundamental parameters. The matter and energy content of the universe are described by 3 numbers. One is the cosmological constant. It's a little bit of a surprise, but not too much, because this was the first type of energy Einstein envisaged to be relevant in the universe. I'll explain that a little in a moment. The dark matter, which I used to think was extremely mysterious. It's one of the big puzzles in cosmology. But recently I've come to believe that there is actually a highly economical explanation of the dark matter. And finally, the ordinary atomic or nuclear matter, which we're made of, and the abundance of that matter in the universe. That's another parameter. On top of that, there are 2 additional parameters. One is the amplitude or strength of these density waves, which came out of the Big Bang. It's approximately 1 part in 100,000. The variation in the temperature from place to place coming out of the Big Bang. So the radiation we see is at 3 degrees Kelvin, but the fluctuations are about 30 microkelvin. It's about 1 part in 10 to the minus 5, it's just one number. And then there's a slight red tilt, telling you that the fluctuations are ever so slightly stronger on longer wavelengths as you look to longer wavelengths in the universe. That's it. Okay, that's it. There is no other conclusively measured parameter there's no evidence for anything beyond this. No strong evidence. Okay, there's slight anomalies here and there. These may strengthen and become compelling, but at the moment, this may well be the full story. Now, in contrast, our theories could not be more complicated. People talk about a multiverse, they talk about extra dimensions, and 10 to the 500 possible universes, and chaos on large scales. That's not what we're seeing. Okay? And so I've come to believe that what we need is a truly minimal theory that's highly economical, and it should be judged on whether or not it explains these numbers. Okay, that's a tall order, but I'm going to tell you about a theory which at least explains the last two numbers from first principles. What is the red tilt? I said it means the longer waves are slightly stronger. To make that a bit more precise, it means that if you go to wavelengths which are 7 times longer, then you get 4% greater amplitude. So not much. Why 7? Because 7 is the square of E, and this tilt is 0.04. This holds over a very wide range of scales, okay? And one of my assumptions towards the end of the talk is that that would hold over a truly vast range of scales, all the way from the Planck length up to the scales we observe. If so, this is an example of critical phenomena. Critical phenomena are what happens when systems go through a phase transition. An example is critical opalescence. You see this in very strongly heated water, that at high pressure, if you heat water strongly enough, what happens is it turns into gas, but the gas and water, that very hot water and the steam are indistinguishable. And you go through this funny phase which has very long-range fluctuations. And that's exactly what we see in the universe. It's very long-range fluctuations with a particular red tilt. And this is a classic example, if true, of a critical phenomenon. Here it is in the lab. You see this. This is a mixture of liquid and gas. At high pressure, you heat it up. This is the opalescence. Has these long wavelength fluctuations which make it slightly opaque to light. And then if you go further, it becomes completely clear, superheated liquid. So, just one example, but this is really everywhere. This type of phenomenon is really everywhere in physics. So it may be that what we're seeing is somehow critical behavior at the Big Bang, which is pretty exciting, if true. Now, this was a very expensive picture made by the world's, by the Dark Energy Telescope. There is actually a telescope, Dark Energy Survey. There's such a telescope, cost millions of dollars. This is what it saw. That's the dark energy. So dark energy is the simplest form of energy. It's absolutely uniform in space and time. It's immutable, unchanging, and it's a constant. And that's why Einstein introduced it into his equation as the very simplest type of matter which might be relevant to cosmology. And he was lucky. It turns out that most of the energy in the universe seems to take this form. The strange thing about it is it's gravitationally repulsive, And so, in contrast to ordinary matter, which attracts under gravity, this repels and causes the universe to blow up. And there's this rather beautiful cartoon of Professor de Sitter, who solved Einstein's equations with a cosmological constant, and lambda is the symbol we use for the cosmological constant. So he's in the shape of a lambda, and the question, it says, what makes the balloon blow up? That is done by the lambda. There can be no other answer. And so people knew about this in the 1920s. It's a very old idea. Now, I'm going to, so I've introduced some of the ingredients. Dark matter is not the cosmological constant. It's some kind of matter which clumps gravitationally. People are often a bit suspicious of that in cosmology. Why do you introduce some weird form of matter and then assumes it clumps under gravity and so on? They're right to be suspicious. But actually, due to the recent observational developments, we can now actually see this dark matter using gravitational lensing. So as the light is emitted from this surface, the hot surface, to us, it travels through this distribution of matter on the way, and that deflects it through lensing, literally by gravity, bending of light by gravity. And so you see this lensed pattern is what we actually measure. And through measuring that pattern, we can infer what the dark matter was doing. And so this has recently been done, just this year. Another telescope looking at the radiation from the Big Bang and inferring this distribution of dark matter. And so here's the actual projected density of dark matter along the line of sight all the way back to the Big Bang. And so now we can actually literally see that, much as you see a drop of water on your fingertip, if you look at a light behind it, you see it by the bending. The water's transparent, but you see its effect bending the light. This is the same effect, but the gravity is doing the lensing. So we can see this dark matter. We still don't know what it is, but I'm going to tell you what it is in a minute or two. Now, of course, there's a gigantic puzzle that the whole thing, the Big Bang that we live inside, seems to have originated at a point. It seems that everything we see traces back to a single point 14 billion years ago. And that's a massive surprise. And again, what I'm going to claim is that by dealing with this strange point and making a very specific hypothesis about it, many of the puzzles in cosmology get resolved. So before we do that, I want to tell you a little bit more about microscopes. Microscopes are obviously how we see the subatomic world. Large Hadron Collider is the greatest microscope ever built. But these cosmological measurements are even better microscopes and potentially take us all the way back to the Big Bang and this special point. So let's just talk about microscopes. Here's a page from Heisenberg's book on quantum mechanics. And I just want to give you an impression of how he argued for uncertainty, the uncertainty principle. It followed from Planck's observation that light had to be quantized in energy packets. Okay, so I'm going to explain. Now, actually, Heisenberg's explanation he attributes to Bohr down there. And one thing about Heisenberg is his diagrams really weren't very good. This isn't even horizontal. Nor does it really tell you what that X means. But anyway, it's an amazing argument. The basic point about the uncertainty principle is that waves spread. Okay, and you can convince yourself of this just by taking a stick and poking the surface of a lake, like Silver Lake outside here. And when you poke the surface of the water, you get waves which spread out. If you try, imagine you tried to emit a wave going in one direction. Okay, that's impossible to do with a stick. if you just use the point. Okay, so you poke the point in, all you'll get is a spreading wave. It won't go in a single direction, it'll spread out in all directions. And the only way to get it to go in one direction is to use the stick sideways. Okay, so where the stick is extended like this and you poke it into the water, the wave will go forward in that direction, but of course it'll spread out at the ends. That's called diffraction. That was well known as a wave phenomenon. If I send a wave in to see some object, the structure here is supposed to be the microscope. So I send a wave in, it's an object of size delta x, but what's going to happen is the waves will spread, and they spread by this amount. The angle of spreading is just the wavelength over delta x. And so intuitively, it's sort of obvious, you can't see an object smaller than the wavelength of the light. But what actually happens is the light comes in, it jiggles the object then re-emits or scatters the light, and it does so in this way that spreads. So this was all very well understood before quantum mechanics. But I think it's a nice physical illustration of the uncertainty principle. This is something you cannot possibly violate, and you cannot possibly make a planar wave by sticking a point into a pond. However, I just told you that the light actually is made out of particles. It's made out of these quanta, or photons. And the problem is that particles kick. So this light wave is coming in, and it's actually a packet of energy. And now you're telling me that that packet is going to spread according to the wave. And so the packet could be deflected through this angle theta. And when it's deflected, that gives a kick. Okay, so the light was actually, this particle came in, hit the object you're trying to see, and got spread out. We don't know where the particle is. It could be anywhere in that spread. That's random. That's what quantum mechanics says, that the precise angle it goes is random. But because it can be deflected by any angle, it kicks the particle. And basically what that means, you can go through the algebra, it means that the uncertainty in the position of the particle you're measuring multiplied by the uncertainty in its momentum is equal to Planck's, or approximately equal to Planck's constant. And so that's Heisenberg's uncertainty relation. It's a direct consequence of the fact that light comes in packets and that light is a wave and spreads. So this was one of a number of thought experiments which Heisenberg and others went through to convince themselves that this uncertainty principle could never be violated. And it's very, very drastic. It leads to all sorts of changes in the laws of physics with respect to classical physics. Now, a slight extension of this microscope picture is to ask yourself, what is the smallest possible object I could ever see? What's the smallest possible length I could ever see? So let's send in a very high energy, short wavelength packet of light, and what happens? So it comes in, it's going to collide with the object you're measuring, and the problem is you've packed a vast amount of energy into a tiny region of space. And when that happens, you get a black hole, because it self-gravitates, and space-time literally falls inwards, and you get a black hole, and unfortunately your microscope doesn't work. So you can't see any length smaller than this length, because the light simply wouldn't escape to be seen. So this is the Planck length. And if we believe Einstein's theory of gravity, and we believe quantum mechanics, this is unavoidable. The largest visible length, there's also largest visible length. I've told you about lambda and how lambda has repulsive gravity. And it's just the opposite. It's just like, in this case, we're inside this special surface. Lambda causes the universe to expand in an accelerating fashion, and that creates what we call the lambda horizon. Anything further than a certain distance, we will never see. It may emit light, but that region is being accelerated away from us so fast that any light it emits will never, ever reach us. And so this is the largest visible length. And actually, that's not so different than the size of the region we now see in the universe. So gravity in both cases fixes the smallest possible visible length and the largest one. So coming back to microscopes, here's the Large Hadron Collider. And this was its big discovery, the Higgs boson, which I'll show you more about in a moment. And my colleague in Edinburgh is Peter Higgs. He's the person who postulated the Higgs boson. He's standing there like he understands what's going on. And I guarantee he does not. He, like me, is a theorist. Theorists spend our times worrying about the concepts and the issues of principle. And it takes real people to build vast practical people to build experiments and to test these ideas. And amazingly, that is what they did. It took about 50 years of continuous development to build a Large Hadron Collider. And when it was built, the Higgs boson was there exactly where it was predicted to be. So this now is all known physics, summarized in a single equation. We have gravity, Einstein's theory of gravity, all the forces like electromagnetism and the nuclear forces. We have all the particles described by Dirac. And Higgs is very lucky. He gets three terms in this equation. The last one includes the lambda. I want to point out some things. You'll have noticed that Planck's law, following Boltzmann, included an exponential, e to the minus. The laws of quantum mechanics are the same, except now there's an imaginary number, I squared is -1. But again, we get this exponential with an imaginary number, and here's Planck's constant h. Actually, it's h over 2 pi is h bar. But these are all the laws we know. And my current point of view is maybe that's all there is. There is no evidence for anything beyond this. And maybe the real challenge in physics now is to calculate all natural processes using these laws. Maybe it's changed. Maybe there are no new particles. And I'll justify that in a moment. So key points to remember: there's an I in here, this strange imaginary number. And there are these particles, like the electron and the quarks that our atomic nuclei are made of. The rest of it are all, in a sense, connections. And this is a precise mathematical term, a connection. A connection tells you how things travel and how they affect each other. And that seems to be that everything else is a connection. You have particles, and then you have gravity, which connects them, and you have electromagnetism, which connects them. And so that seems to be the underlying logic in the laws of physics. So here it is in more detail. We have quarks that atomic nuclei are made of. We have leptons, like the electron, like neutrinos. And the Higgs boson, which couples to everybody, as does gravity. And then we have these forces, the strong, weak, and electromagnetic forces. And that seems to be all there is. Now, so these are all the particles that we've discovered in accelerator laboratories. As I mentioned, CERN has not discovered anything beyond these yet. There is one. These are the left-handed neutrinos. You'll notice the L here. We've only ever observed left-handed neutrinos. Left-handed means that as it's traveling along my thumb, it's spinning this way. And that's the only ones we've seen. However, now we want to solve the problem of the dark matter, okay, to start off with. What is the dark matter? So, I should mention one other thing. There's a puzzle. There are 3 generations, right? So this pattern, up, down, electron, neutrino, is copied 3 times. That's quite strange. Why is that? We don't know. I'm going to tell you that there is an explanation now. It's part of this new theory that we think this was forced on you mathematically by the principles of the theory. But that's a puzzle. Now, the left-handed neutrinos are not going to explain the dark matter. We've observed all of them, and they have tiny masses. But turns out there's a simple fix. Just delete the L. Okay. All right. So imagine that electrons, like the other particles, come in left and right-handed versions. Imagine that. So you've just got to add the right-handed partners to the left-handed neutrinos. That's a very modest change in the standard model. And it's suggested by symmetry, because now everybody has a right-handed partner. Okay? So that is the most obvious extension of the standard model. It was proposed in the 1970s, and it's probably true. Why is it probably true? Because if these right-handed neutrinos are heavy, we wouldn't have seen them in experiments so far, but they do explain why the neutrinos we see have a tiny mass. Okay, they're not massless. It turns out that the neutrinos can travel along, couple to the Higgs, and transmute into a right-handed neutrino. This is very heavy, and so it requires a lot of energy. So you can't stay a right-handed neutrino. It's a virtual right-handed neutrino. You oscillate into this for a very brief moment of time, basically the inverse of the mass of this right-handed guy, and then you have to oscillate back into a real neutrino. So the left-handed ones would mix ever so slightly with the right-handed ones, and the heavier the right-handed ones, the less the mixing, because it's just, it's harder and harder to oscillate into a right-handed neutrino if it's, the more massive it is. So this is called a seesaw mechanism. The heavier you make this, the lighter you make this. And what we realized recently is that these right-handed guys are just the perfect dark matter candidate, because they don't couple to light or the other forces we know about. They only couple to gravity and to this Higgs. So these right-handed neutrinos could be the dark matter. And we found that we could explain. So now this starts getting cosmological. Okay? The question is, how do you explain their abundance in the universe? What would explain it? And we found an explanation of their abundance if we assumed the universe was invariant under another symmetry, which is called CPT. So CPT is the most fundamental symmetry known in physics. It says if I take a system, and for every particle, I replace it with its antiparticle, and I invert space, and I reverse time, that has to be a symmetry of the system. I get some other system, but it will behave in the identical manner. Okay, so there's the CPT symmetry. Our hypothesis is that the universe itself respects this symmetry. It's a symmetry of the fundamental laws. The universe could either respect it or violate it. What if it respected it? If it respected it, then for our matter part of the universe, we've got more matter than antimatter in the visible universe, there has to be a partner which has more antimatter than matter. Time would go in the opposite direction for the partner. But then the amazing thing is that the size of the universe, when it shrinks to 0 at the Big Bang, it does so linearly in time. And if it's shrinking linearly, if the scale factor is shrinking linearly, you can just extrapolate it. It's called analytic continuation. It's unique. And basically, you can continue the right-hand side uniquely to the left-hand side through the Big Bang singularity. Okay, so that's a possibility. If you do that, it turns out you predict the abundance of the dark matter. Oh, I should say, you see, doing this is like the method of images. in physics, if you have a mirror and you want to solve the equations for light in the presence of a mirror, there are two ways to do it. Either you figure out how much light is leaving your face, it bounces off the mirror according to prescribed boundary conditions at the mirror, and then it comes back. Or you do something simpler, which is you just make a carbon copy of yourself, and if you're right-handed, you make it left-handed. On the other side of the mirror, you throw the mirror away, and you just follow the light from one copy to the other. That's what this is doing. Okay, so it's just the method of images applied to cosmology in order to impose a boundary condition here which respects CPT. So there's no reality to the pre-bang universe. It's just a convenient mathematical construction. So in this viewpoint, the Big Bang was a mirror, a special kind of mirror, but it's rather unique. It's a type of mirror that respects the basic symmetries of the laws we know. The right-handed neutrinos turn out, in this picture, you can calculate how many are produced. They're produced as Hawking radiation from the Big Bang itself, and we can predict exactly what their abundance is. There's one adjustable parameter, which is their mass. If it happens to be this big, which is much bigger than the mass of a proton, they account for the dark matter. And this is the simplest yet explanation. Doesn't mean it's true, because I need some evidence. I need to make a prediction and verify it. Fortunately, there is a prediction. If one of these right-handed neutrinos, and there are three, like the other left-handed neutrinos, if one of them is stable, it implies that the lightest neutrino is exactly massless. And you can see that from this picture, because if the right-handed guy is stable, it means you must switch off this vertex. Otherwise, it would decay into left-handed and Higgs. Okay, so we switch off that. But if we switch off that vertex, we also switch off this. It's the same vertex. So this left-handed neutrino cannot mix with right at all. So this one is massless. And so that's the prediction. And amazingly, this is now testable, that the masses of the neutrinos are now being measured through their influence on the clustering of matter. And so the best galaxy surveys now, one called Euclid, it's a satellite, a European Space Agency satellite, and the large-scale survey of space-time in Chile, these surveys are now measuring the clustering of galaxies so precisely they should be able to test this hypothesis. So we'll see. Either it's true or not. If it's true that it's massless, then this becomes easily the most convincing theory of the dark matter, in my view. Okay, so I've returned to this. The Big Bang, the hypothesis is the Big Bang was a special type of singularity. Scale factor vanishes linearly. This was anticipated by Roger Penrose, who was mentioned earlier in the 1970s. Penrose made the hypothesis that the initial singularity, this thing where all of space shrinks to a point, is what's called conformal. Now, conformal means that light doesn't see it. Okay, light waves, you see they come in all wavelengths. They're all basically copies of exactly the same thing. And light itself does not know about the size of the universe. The equation it follows is independent of the size of the universe. So light is conformal. And Penrose's hypothesis was the Big Bang was conformal. And if everything in the universe behaved like light at the Big Bang, then actually nothing would be aware, none of the matter inside the universe would even be aware there was any singularity, because they don't care what the size of the universe is. So conformal is like this. If I take a square grid and I try to push this into a circle, I try to distort the square boundary into a circle, I can do it in such a way as I preserve angles. So this is what's called a conformal mapping. And if you look carefully, you'll see that the angles at all these vertices are exactly 90 degrees, even though the whole shape has been distorted. And essentially because light or photons only cares about angles and not the overall scale, it wouldn't be aware of any difference in this situation. So that might be the Big Bang singularity in one picture, but if you stretched it out, it's perfectly regular. So here's Roger Penrose giving a perimeter public lecture some time ago. And yeah, it's my honor to have a visiting chair in his name. Amazing individual. And here's his, one of his beautiful pictures. Penrose has emphasized the difficulty in explaining why the universe is so simple on large scales, right? As I mentioned before, in every direction we look in the universe is practically the same. It just varies by these random waves, whose amplitude is only 10 to the minus 5. So it's essentially very uniform, very isotropic, it's a very, very special geometry. It's not wild and convoluted at all. And so here's the creator making the universe and picking this extremely special geometry, the one we see, for the universe to be in. And he emphasized what a puzzle this is. So what I'm now going to claim is that I think we have a solution to that puzzle. We know why the universe is so smooth and simple. And the reason is, I mean, it involves some extrapolation of ideas of Stephen Hawking and others. But the reason is essentially the same as the reason that the gas in this room is homogeneous and isotropic. You know, why are the air molecules so smoothly distributed? And it's a good thing they are, because if they all flew off into a corner, we wouldn't be able to breathe. Okay? They don't do that. And why not? Just randomness. It's just that there are a lot more possibilities for the molecules to be smoothly spread out than for them to all be in one corner. It's entropy. Maximizing entropy explains the homogeneity of air. It's thermodynamics. You don't need a mechanism. It's just what happens most of the time, the vast majority of time. So I'm going to show you now we have an explanation for the large-scale geometry of the universe which has a similar character. It's thermodynamic, doesn't require a mechanism. So it's based on Stephen Hawking's ideas. So he was interested in black holes. And black holes are these wonderful objects which in a sense are like giant elementary particles. They have very few parameters. They're totally smooth. They can have a spin, they can have a charge, they can have a mass, and that's it. They're just absolutely featureless objects like an elementary particle, but they can be huge. They can be, we've seen black holes of hundreds of solar masses in size. So, actually much more than that, millions of solar masses. A black hole has a temperature, which is called a Hawking temperature. And so this was a huge surprise that black holes are slightly hot. It's a very tiny temperature, but they're slightly hot. More importantly, they have an entropy. And roughly speaking, it tells you the number of ways you could have made that black hole. And the entropy is proportional to the area of the surface of the black hole. Here's Stephen Hawking at perimeter when it was the Stephen Hawking Center was under construction, and he visited a number of times. Was treated exceptionally well in the bistro, I must say, which he enjoyed, and was absolutely inspiring to have visit. Here he is with somebody else you may recognize, the founder of Perimeter Institute, Mike Lazaridis, and we're out on Lake Huron during one of Stephen's visits. They both look very cool. So Hawking used a very profound mathematical trick, which I mentioned this I, this imaginary number, that distinguished the Boltzmann type, the thermodynamic arguments from the quantum arguments. And Hawking used that trick to relate the two. And the way he related them is by making time, by calculating in imaginary time. It sounds very speculative, but it's not. It's a very precise technique. And so he used imaginary time to calculate the Hawking temperature and gravitational entropy of a black hole. Now, essentially what he did is he took the space-time of a black hole, which is a function of which has a certain description in terms of real time and real space, and he said, what if time goes imaginary? It turns out when time goes imaginary, the black hole is actually periodic in imaginary time. It repeats itself in imaginary time, and that's the signal of a temperature. If you have a system which is periodic in imaginary time, the period actually defines the temperature, and that's at least one way to calculate the Hawking temperature. And the entropy calculated similarly. So recently we were able to do the same for cosmology. Okay? Calculate the Hawking temperature and the entropy for cosmology. I'll show you a simple example first, and then I'll show you the general case. So this was done by Hawking and collaborators. A cosmos with only lambda. This, in fact, was Einstein's first model of cosmology. Let's only have lambda and gravity. Well, it's repulsive, and so the universe, if it's a big circle in this case, I'm only plotting one dimension of space, so it's a circle, it shrinks and re-expands because of the repulsion. Okay, that's called de Sitter space-time. And when you make time imaginary, the space-time, time goes up, the time now becomes periodic. And so this is the gravitation, what Hawking called a gravitational instanton. It's the imaginary time version of de Sitter space-time. It has a temperature, which is just the length of a great circle on that sphere. And it has an entropy, which you can calculate. So recently, we were able to solve Einstein's equations for general cosmology with radiation, matter, curved spatially, and lambda analytically. And we discovered it looks somewhat like this. It's not a sphere anymore. It's distorted. And so here's the imaginary time cosmos from which you can calculate the entropy. And the real-time cosmos you can think of sort of sprouting out of the imaginary one. Why this is interesting? Because it turns out that this gravitational entropy, if it is an entropy, just like the entropy of gas in a room, it tells you which cosmologies are more likely. And the ones which are most likely, according to this formula, are spatially flat, just like we see, homogeneous, isotropic, and isotropic. And secondly, this calculation also favors that the cosmological constant is small and positive, which is just as we see. So this is still very new. We're arguing with lots of other experts what this means. But in my view, this is a thermodynamic explanation for the large-scale geometry of the universe. So we don't need smoothing or flattening mechanisms. Some of you may have heard of inflation, which is a postulated period of very rapid expansion just after the Big Bang singularity. We don't seem to need that. Now, our telescopes are also microscopes. And as we look out in space, we are looking back in time. The universe is shrinking. That's what this picture shows. So currently, the radius is 20 gigaparsecs, let's say. If we shrink that region back to the Big Bang, it's about 10 microns. And then if I take that same region and follow it forward into somebody's eye, that's what we see. So this is the largest visible region of the universe, the one in green. Of course, as we're looking backward in time, the universe is smaller. What that means is that a structure that was only a Planck length, or a wave that was only a Planck length across at the Planck time, the smallest conceivable length, right now would be about 1 millimeter across. It would have expanded to about 1 millimeter. If we can capture gravitational waves from on millimeter scales, literally we can look at the Big Bang. We can look at the singularity. So that's very exciting. This is still, these are being developed. It's very likely going to be decades before this is feasible, but there are actually prototypes already. So I want to now explain, what I'm moving towards is explaining two things. One, why there are three families. I told you that would be explained. 3 generations of particles. And two, where did these waves, the density waves, come from that we see in the sky? Okay, did they somehow originate at the Big Bang singularity itself and then move forward and end up creating, leading to the formation of galaxies and stars and so on? Okay, so I'm going to explain that. Now, to understand that, we have to understand how the standard model couples to gravity. And currently, there's a very fundamental paradox in that coupling, which is that the standard model fields, electromagnetism, the electron fields, all the other fields, fluctuate in the vacuum, in empty space. The reason for those fluctuations are basically the Heisenberg uncertainty principle. If you try to set them 0, then if you set essentially their position to 0, their coordinate, how the amplitude of the wave to 0, then its velocity is indeterminate. You cannot set them to 0 and be consistent with this Heisenberg uncertainty principle. This is a picture of what's going on in the vacuum right now, with either, this is actually for the strong interactions, but it would be the same for electromagnetism or other fields. Unfortunately, the energy in these 0-point fluctuations is infinite, okay? And that's a problem, because how do you couple it to gravity? So we have various procedures to ignore that, but they are rather artificial, and they leave you very confused. Somehow, something's going on in the vacuum which seems deeply paradoxical. They also turn out to spoil this conformal symmetry, and so therefore we cannot describe the Big Bang. So our starting point was actually to take a clue from cosmology. What kind of field, if it fluctuated, would lead to a pattern like the one we see on the sky? And it turns out there's a unique answer. It's a dimension 0 field. It's basically a field that is dimensionless. Okay, so if you ask for its correlations of this field, it correlates there's no scale. Just like the fluctuations we see are roughly the same strength on all scale, that's what this field has. And actually, these fields had been thought of before, and they were shown to be a simple gauge theory in the 80s. So here are the standard model particles. What we discovered is if we add 36 precisely of these extra dimension 0 fields, and you may wonder where the 36 comes from, and a clue is that there's 6 of these and 6 of those, but I'm not going to say any more. Turns out these exactly cancel the 0-point energy. And they also restore the conformal symmetry, right? These are highly non-trivial cancellations. And furthermore, it only works if there are 3 generations. Okay, so this is a very new discovery. We're trying to still make sense of it. These dimension 0 fields are peculiar because they just change the vacuum, but they don't have any particles. Okay, so not adding anything, you're just adjusting the vacuum of the standard model so that it doesn't have these violent energy fluctuations, and it's consistent with this conformal symmetry that would allow you to describe the Big Bang. Based on this, we were able to predict the amplitude. And here it is, the big formula, but you see it all sorts of pi's and 5's and numbers, the number of degrees of freedom in the standard model. These alphas are couplings, which are measured in experiments like CERN. But the principles I've explained, that we want this conformal symmetry, and because we want to describe the Big Bang, where apparently the universe was at 0 size. So we worked out all these numbers. This one in particular is interesting because alpha 3 is the strong coupling constant. We extrapolate it to the Planck scale. It's a huge extrapolation in energy. And it turns out it is what is called a critical exponent. In other words, I told you there was a tilt. Waves get slightly longer as you go to long wavelengths. This is how much stronger they get. And this tilt has to be compared with 0.04. So it turns out we plugged in this number from the CERN measurements, extrapolating the CERN measurements to the Planck scale, and this number is exactly very close to 0.04. So our prediction is 0.042. This is the measurement from the Planck satellite. So that's just a first principles explanation. A lot more theoretical work is needed to confirm this, to calculate corrections, make sure they're under control. Observations are also improving. If this agreement holds up, then the theory will become compelling. So it may be that we have an explanation of all this. It's all basically in the physics we know, is that we have to do something to fix up the vacuum a little, but otherwise cosmology is all under control. So thank you for listening.
All right. Thank you, Neil.
Thank you.
So captivated, I almost forgot to stand up to do the Q&A. So we will now take some questions both from the online audience and from the audience here. If you have a question, please come down to the microphone that is set up here on the stairs. And we'll just go with the queue, and I'll bring up the online questions as well. So if you're online listening, you can add a question with the hashtag #PILive. So we'll start, while we let people come down, we'll start with an online question. So let's see, what do we have? Here's one. So I think this is a fun one to start with. Would the mirror universe be an identical reflection to this one, with a mirror Earth moving with a mirror Neil Turok giving a mirror lecture?
No. So the thing is, you've got to clearly distinguish classical from quantum. Now, a quantum geometry is a fluctuating thing. So when I draw this geometry, you shouldn't really picture a single geometry. You need to picture something that's a bit fuzzy, and it gets more and more fuzzy near the singularity. When the universe is small, that fuzziness means that the quote singularity could actually be moved around. There's some fuzziness. The way you impose this CPT symmetry is on where the universe is large. Okay, so it's, if you like, this is a two-sided universe going out on either side. You impose a symmetry that if I turn the whole thing around, there's no difference. In both cases, there are fluctuations. So it's really the CPT symmetry is a quantum symmetry, and you shouldn't think literally that the two sides are carbon copies of each other. I think of it more as a sort of mathematical device to do something sensible with the singularity, and you don't do it at the singularity. Instead, you picture this extended space-time and impose a symmetry on that. If you flip it around, that's what you do.
Thanks. All right, we have a question from the audience. Go ahead.
Hello, I'm not me. I'm my soon-to-be 87-year-old mom, Doris Matthews from Elmira, 14 years into Alzheimer's, and her third-generation great-grandchildren. The universe from within, from quantum to cosmos. Everything is a spring, high-frequency compression to low-frequency expansion, harmonic oscillation. Everything in our neighborhood. I'm a kid, 1940, 2040, an imaginary time. Little girl, in our park, having a ball, seesaws, waves in our sandbox. It's a blast. Is it true? The universe is made of stories, not of atoms. Tell me, so I could tell my mom and dad, and we could tell our neighbors right here, where we play, in our park, where Mother Nature teaches us everything. We can't wait. This is Waterloo, our region, our perimeter. We are you, you are us. We are one, connections. We are the Big Bang, the game of life. Come and play. Everything's A-OK. Our way to where the air is sweet, Mr. Turok. Can you tell me how to get to Sesame Street?
Please thank her for that. I should mention that one of the most remarkable meetings I ever witnessed was between Stephen Hawking and Sidney Poitier, who of course was a legendary actor. And they sat across the table from each other, and Sidney said, "Let me tell you what I think the universe is." And Sidney indeed had his own theory. He didn't have mathematics and so on, but he absolutely had a vision as to how he thought things should work. And it was just absolutely fascinating to see the passion with which he communicated it. And yeah, Stephen was pretty blown away by Sidney. So yeah, we all have our pictures. And she's absolutely right. This is nothing but a story. All of physics is just a story. Somebody at our conference this afternoon spelled it out very well, said it's a narrative. Physics is a narrative. It's something we tell ourselves about the way the world behaves. The extraordinary thing about physics is that when the narrative converges, we can use it. And it has incredible power. So, but in the end, it's just a story.
Excellent. All right, we have another question from the audience. Go ahead.
Thank you, Professor Turok, for the talk. I appreciate it. I have two questions. One is, when we think about the Big Bang as happening 13.8 billion years ago, it seems like relativity tells us that time is relative. So can the Big Bang be envisioned as something that's constantly happening, like it has its own spin, like a constant phenomenon? And like the sun you were saying at the beginning, it seems to us like it's 14 billion years ago, but it has its own spin, sort of.
Well, when we say 14 billion years, that is as measured by a particular clock, okay? And the particular clock is an object which was at rest throughout this expansion. So there's a sort of preferred frame in the cosmos, which is defined by the radiation. You can, if you're quote, at rest, and you look around you, you'll see the radiation is the same in all directions. If you move, you'll see difference. So for such a clock, the time it would measure to the singularity is 13.7 billion years. But yeah, I'm not sure I fully understand the question, but it's certainly true that time in general relativity is different objects, different observers see different times. But that we believe we understand. We believe that at the end the story is remarkably simple. What seems to happen at the Big Bang singularity itself is that the notion of time, if this picture is correct, the notion of time becomes meaningless. Why? Because everything becomes light. Literally the only things which exist are light. Light does not see the expansion of the universe. Light does not see time either. If you ask a photon, what's the time? A photon will tell you, I see the whole universe, all of existence, simultaneous. Okay. So photons are pretty amazing things which have no time, no notion of time. And that seems to be, if this is right, how you deal with the singularity. There was no time at the Big Bang, or at least there was nothing around to witness the time.
have a part two? Is that
Yeah.
okay?
Yes.
Thank you. And just because you had that sort of that expansion on like the universe that we observe in your sort of universe sort of mirror model.
Yes.
And I think Penrose had developed the conformal cosmic
Cyclic
cyclic
cosmology.
cosmology.
Yes.
So, I mean, I don't know if that makes any sense from your model, but as the universe becomes all black holes and then the radiation and heat death, would that be where it connects on, like it connects in the middle, but would it connect to the universe at the heat death?
No, I mean, I have the greatest possible respect for Penrose's ideas, and as I indicated, what we're connecting it is an idea of his from the 70s, which is about the singularity. Since then, he started to advocate this cyclic universe picture, I think partly influenced by myself and Paul Steinhardt, because we talked about cyclic, whereas I've abandoned that as too complicated. He is now advocating it. But the problem is that he doesn't really have a way to match the future of our universe to the Big Bang of the next one. He doesn't have a mathematical prescription for how you... He has a prescription, but it doesn't really work. Whereas what we're doing here is called analytic. It means that it's unique, the connection between these two sides. So, but we're in discussion about it. I'm trying to persuade him that your previous idea was much better than this one. But we'll see. I mean, it could well be that he turns out to be right. He has turned out to be right on very, very many things.
Thank you.
Thank you. All right, we have another question.
Thank you very much for the nice talk. I was wondering about one remark which you made about the production of the right-handed neutrinos.
Yes.
And so if I understood it correctly, it would be like a Hawking radiation effect
Yes,
from the early
yes.
universe.
Yes.
And normally Hawking radiation is associated with some kind of horizon
Yes.
or some cosmological horizon.
Aha.
If we are now in this regime of very early times and the
There's
scale
no-
factor is linear,
There's no horizon. Yes, so I meant, okay, so it's good you asked. So at some level, it's totally obvious to suggest the right-handed neutrino is the dark matter because it doesn't couple to light or other forces. Why wasn't this done in the 70s? And the reason was that everybody thought that the abundance of particles are determined by thermal equilibrium in the hot Big Bang. If you switch off this coupling so that it's stable and can be the dark matter, it was never in thermal equilibrium, so they didn't know how to calculate its abundance, so they assumed that wasn't the case. And literally, they made an assumption just so they didn't have to worry about it. Okay. Now, so we did worry about it because we wanted it to be the dark matter. And then when I said Hawking radiation, what I really meant is it's the time dependence of the cosmology that creates the particles. So it's not with a horizon, and with a black hole it's associated with the horizon, but in general, if space changes, the scale factor changes, you produce particles. It's much more general than having a horizon. And in this case, that's what happens. It's just the mere fact the universe is changing in size creates a particle.
thank you.
All right, we have time for a couple more questions. Go ahead.
Hi there. You had mentioned that an explanation for dark matter could be right-handed neutrinos,
Yes.
but that relied on a left-handed neutrino being massless.
Yes.
My question to you is, have we not measured the mass of a left-handed neutrino to be non-zero?
No, great question. So what has been measured, there are three neutrinos, three light neutrinos we know of. The only things that have been measured are the differences in actually the squares of the masses of those three neutrinos. So we know two numbers. We know essentially two differences between the light neutrino masses. We do not know the overall scale. So our prediction is that you have these three masses, and the lightest one is massless. So we predict all the masses from that, from the known measurements. And what these galaxy surveys are going to do in the next 3 to 5 years is fix the sum of these neutrino masses. So if they find the sum is essentially just the sum of those two differences, then it will confirm that the lightest one is massless. So.
Thank you.
That's a great question. All right, let's take one final question from the audience.
Thank you for the lecture. It was amazing. My question is just, you were talking about this sort of mirror universe that is similar to ours at cosmological scales, but not identical because of fluctuations close to the Big Bang.
Yes.
Feynman sort of had this idea of electrons and positrons being not separate particles, but merely the same particle traveling in different directions in time.
Yes.
Could those particles travel between our universe and this mirror universe through the singularity because, a positron and electron collide?
It's a great question. There is this very fundamental view of antimatter as just being matter that's traveling backwards in time. And in fact, Feynman, the greatest expert on all this, made the statement that he believed quantum field theory, which is what we use to describe the Standard Model, was nothing but a way of hiding the fact that particles go backwards in time. Okay. So indeed, this in CPT is, you see, if I have a particle traveling from A to B with a world line, and that, let's imagine time goes up and space sideways. So the particle can go forwards and backwards in time and so on. What is CPT? It's just reversing the arrow on that line. So instead of going from here to there, it goes from here to there. That's CPT. And indeed, that must be possible. Okay, so somehow we're doing the same thing with the cosmos. But one way of picturing this two-sided diagram is that it's really a U shape. And you can imagine a universe going backwards in time for a while and then turning around and going forwards. Reconciling these pictures of the particles and the universe is something we still have not done. And it should be fruitful, but I don't quite know how to do it yet.
Still working on it. Thank you.
Thank you.
Okay, you have a quick question?
Okay, yep. I was sitting there and I was thinking, this is very complex. And I can understand why you haven't come back from Britain, because you were having too much fun. But I'm thinking that if we start from the very basics, existence, what is existence? How did it appear? I mean, we're sort of going after the second step,
right,
of looking at the ball bearings in the world.
No, you're absolutely right. The more basic the question, the harder it is to answer. So all physics is doing is sort of following our nose and trying to figure out what might we learn next. But the motivation is exactly what you say. We're trying to understand what the hell is going on.
Right? Why?
In a very big sense.
Why is there existence?
We don't know. The best we can do is...
That should hint to what all these molecules and everything is about.
It would be called enlightenment.
That's a lovely thought to end on. So thank you very much, Neil.
Thank you.
Thank you.